Yeah. Today we are on to section 3.3, and we are going to start talking about logarithms. This is logarithmic functions and their graphs. A logarithm is an inverse of an exponential function. So we have y equals b to the x. We're going to keep it a basic one, no transformations on this. So that's why the a is not here from the ab to the x. To do an inverse, I think we've talked about inverses already this year. I switch x and y. Yeah, we've talked about inverses. Well, to solve for y equals, I end up using what's called a logarithm. And we convert from exponential form to logarithmic form. So here our exponent y, this is exponential form. Our exponent y becomes what it's equaled. The base of the exponent, b to the power of y, becomes the base of the logarithm. And the brain, what it equals goes inside the logarithm. So this is logarithmic form. Logarithmic form. There we go. I think I've spelled that correctly now. So graphically, my exponential looks like this. Oops. That x needs to be an exponent. A inverse is a reflection over the line y equals x, which looks like that. So this looks roughly like this. We'll talk a little bit more about some key points later, but there we are. Example 1 does some conversions. Or functionally, we're going to evaluate some logarithms. So we have log base 2 of 8. And if we're told to evaluate it, we can use a calculator. I'll show you that in a little bit. But here we are. We'll say it's x. So that means 2 to the x equals 8, which is 2 to the third equals 8. Log base 3 of square root of 3. And again, we'll put in an equals x, convert to exponential form. That is the 1/2 power is the same as the square root. Log base 5 of 1/25. And we'll say x, 5 to the x equals 1 over 25. That's like 1 over 5 squared. And 1 over means a negative exponent. So 4 to the x equals 1. That's 4 to the 0. Oh, log any base, because anything to the 0 power is 1. So log any base. Doesn't matter whether it's base 4. We pronounce this log base 4 of 1 equals x. Doesn't matter what the base is. If it's of 1, it will always be 1. So again, I'm inserting the equals x every time. 7 to the x equals 7. That's 7 to the first. Okay, couple of things to note about logarithms. Log base b of b to the 7th equals 7. These are inverse operations, log base b of b to a power. These are also inverse operations. B to the log base b of 7 also equals 7. We can abbreviate the base 10 log by just writing log. And I'm sure you've seen that in science classes before. You've seen it in algebra 2. We can also abbreviate log base. We've talked about the number e already. E being the natural base of the exponential. ln, it's known as the natural log. There's a beautiful thing come calculus. So let's talk about how to evaluate a few logs on your calculator. There's a few that we can do by hand, but we're going to talk about doing them on the calculator. We're going to skip to example 4. And I don't need the graph here, so I'm going to clear out of the graph. If you're doing a base 10 log, you have a log button right here on the side. The first one is log of 34.5. That's 1.538. Right here. I usually am going to go 3 decimal places. Okay. If we need to do a log of a base that is not, and I repeat, not a base 10, there's 2 different ways to do this. First one is click on the math button. And you go down, I kind of scrolled to the bottom and then back up to log base. Log base 5 of, this isn't really one of the examples, but log base 5 of 17. That's option 1. Option 2 is to use what we call the change of base formula. If you forget about log base, you can do this one. And I usually change the base 10 logs because they're easy. And I do log of the number 17 divided by log of the base. I'll show you that that's going to equal the same thing. Important that I close my parentheses, though. Oh, hey, look, the change of base formula does actually work. So either one of those works. I made it through high school without the log base button. It didn't exist on my calculator. That is a nice new feature they've got. So we can solve pretty simple logarithmic equations. This is going to be example 5. Log x equals 3. Remember, it's not written, but it's here. So I convert to exponential form. 10 to the 3rd equals x. 10 to the 3rd is 1,000. Here's another one. Log base 2 of x equals 5. 2 to the 5th equals x. X equals 32. Example 6, we're going to do the same thing, but with natural logs or ln's. So this one, when you're not comfortable with ln's, it's not a bad idea to write log base e. Square root of e is e to the 1/2. Hey, base and the power to a power, or the base of the log and the base of the exponent match. Inverse operations, that's just 1/2. Oops. Next one. ln of e to the fifth. Again, log ln of e to the power, I just keep the power. E to the ln 4, e to the power of, and ln or natural log are inverse operations. It's just 4. I can show you a natural log on a calculator. The natural log button is right below the log button over here on the side. I highlighted it there. You just type in your number and you get 3.157. So that's using my calculator. Got a couple more examples. We're going to talk about graphs. I'm going to graph the ln function here. I guess I got a bunch to clear out here. ln x. Zoom standard. And we see the graph. It's important to note that even though you don't see it here, this does keep going down like this. And that is a vertical asymptote at x equals 0. It's the y-axis. So when I do my analysis, I've got domain. 0 is a vertical asymptote, so that's not included. It goes to infinity. The range, on the other hand, is negative infinity to infinity. Notice these are exactly swapped of the exponential function. Continuous. Yes, from 0 to infinity. Can we map that off to x? Increasing. 0 to infinity. Decreasing. Never. Symmetry. None. Oops. Boundedness. None. It is not upper bounded. It will continue to grow just very slowly. Extrema. None. Asymptotes. That's x equals 0. End behavior. It does not approach. Negative infinity is not part of the domain, so I don't have an end behavior for that. Limit as x approaches infinity is infinity. Doesn't get there very quickly, but it does get there. And do not include negative infinity when it's not part of the domain. Okay, we're going to transform a couple of graphs. So we're going to go back to the whiteboard and I'll sketch them. So we start with y equals ln x. Looks like this. Goes through a couple of key points. No, not 0, 1. 1, 0. Because the ln of any number or the log of any number, any base, is going to be 0. And this one is E1. So if I introduce one with a transformation, y equals ln parentheses x plus 2. The plus 2 shifts the whole graph right, left 2. Suddenly I'm over here. My asymptote must also move left 2. And my graph looks like that. This other point, E1, has to become E minus 2, 1, where I've subtracted 2 from that E coordinate. We can get a little interesting here. So ln of 3 minus x is like negative x plus 3. Now to apply my normal transformation rules, I must factor that negative out, but it can't go outside the parentheses in the ln. So that means I shift it right 3, which means my whole asymptote moves right 3. I guess I got that E in the wrong spot here. And my function, nope, it's got a negative, which means I got to reflect over that asymptote. So I would be here and over here, but then I got to reflect across and get about here. So it looks like roughly like that. Okay, now we're going to talk about another one. Now we're going to do a base 10 log. The base 10 log goes through the point 10, 1. It's always whatever base if I change it to y equals 3 log x, I simply multiply each y coordinate by 3. Well, 0, 1, 0, the y coordinate doesn't change. But 10, 3, it certainly does. So we get a slightly stretched out graph. If I have 1 plus log x, I just take log x and I shift it up 1. Which makes it taller at first, but that's transformations. Last thing we need to know is the decibel scale. Decibel scale is similar. You probably saw the pH scale in chemistry. That is a logarithmic scale. The decibel scale, we're going to use the Greek letter beta. And it's measured for sound intensity. This is also a logarithmic scale. The other one is the Richter scale. What does that mean? On a standard logarithmic scale, each increase of 1 represents 10 times as strong. This one, because of the 10 in front, each increase of 10 decibels is 10 times as much sound intensity. Most people tend to interpret 10 decibels as twice as loud, but it's actually 10 times the sound intensity in watts per square meter. If you look at 307, there's some common watts per square meters. Hearing threshold is 10 to the negative 12th. Soft whisper is 10 to the negative 11th. City traffic is 10 to the negative 5. The threshold of pain is 10 to the 0. So that's 100 decibels. No, actually, that's 120. This I0 here is the 10 to the negative 12. Okay. And a jet takeoff is 10 to the third. That is 150 decibels if you're right there. Super duper loud. You may have to use that equation. Okay, that wraps up 3.3.